Good morning, everyone, and thank you for attending this talk. I will be presenting today on behalf of my colleagues who worked with me on this project. So thank you to Allison Gibbs, John Shea, Paul Pacente, and everyone else at Canadian Discovery who helped with this project and putting this presentation together. Allison is also giving a talk focused on liquids in the lower Montney Tuesday afternoon if you are in the mood for some excellent Montney content. As the title suggests, this presentation will be focused on the Clearwater Formation in northern Alberta. On the map to the right, the Clearwater fairways are outlined in green, with the Jarvie Trend located here in the south, the Marten Hills-Nipisi fairway through this area, and the Gift Trend up here. Marten Hills is by far the most prominent area of production in the Clearwater, and recent development shows that the bounds of the play are being pushed to the south from Jarvie towards the canal area, and to the northwest from Gift towards the Cadott area. The red box here demarcates the mapping area of the maps to come. We will begin with a brief overview of regional geology and the history of the play before jumping into the petroleum systems, including the geothermics and potential sources of oil in the Clearwater. We will then go on to hydrodynamics and discuss the dynamic flow system that exists within the Clearwater. We will wrap this up with a discussion of oil quality. Specifically, how can hydrodynamics and thermal history help to understand and predict oil quality within the Clearwater? And why has the Clearwater suffered less degradation than other reservoir units? The Clearwater Formation is often described as a missed play opportunity. Thousands of wells penetrate this zone as operators explore deeper horizons or Clearwater gas plays. With the advent of reliable multilateral horizontal drilling techniques, this play, which was previously hiding in plain sight, is now the main target. Since 2016, and really 2017, there has been a dramatic jump in production from essentially zero to over 23,000 barrels of oil per day as of the end of 2019. Production peaked in February of this year at over 33,000 barrels of oil per day before dropping off drastically in April and May. The play's production is recovering nicely, and current production is back to 2019 levels. The Clearwater Formation is an Upper Cretaceous formation underlaid by the Wabasca and McMurray formations, which sit above the Paleozoic unconformity. The Clearwater is overlaid by the Grand Rapids. The Clearwater represents fluvial, deltaic, shoreline, and offshore deposits that were deposited within an interior seaway. The productive fairways are represented by fine-grained lithic sandstones in shore-face sequences and incised channels. There's currently production occurring from all four Clearwater zones. When we say oil quality, what we are really getting at is what is the API gravity and viscosity of the oil. Oil quality can be affected by several factors, including migration pathways, geothermics, hydrodynamics, and water chemistry. As you can see on the graph to the right, the Clearwater has a large range in oil qualities, ranging from APIs of 11 and over 20,000 centipoise viscosity in the Gift area to APIs of over 25 and viscosities of less than 40 centipoise in the Marten Hills area. Marten Hills generally has the lightest oil in the red data points here, followed by Nipisi, then Jarvie, and then Gift with the heaviest oils. There's also a new data point in the Cadott area, which is further to the north, and this data point has oil qualities similar to that of Nipisi. Obviously, this large range in oil qualities will drastically affect the production and economics of a well. Additionally, there's an oil analysis from a Mississippian to Bolt well just to the west of this Cadott well here with an API of only 6. This is an extremely heavy oil and has obviously been degraded a lot more than the oil in the Clearwater. We also see this with the Wabasca, which again has a lot heavier oil than the Clearwater. Hopefully our look into hydrodynamics will help to provide some insight into not only the Clearwater variations, but also the differences between the Clearwater and other reservoirs in the area. It's also important to note that oil quality is only one factor to consider when determining the productivity of a well. Reservoir quality is also very important, and exploring the interplay between oil quality and reservoir quality is really the key to unlocking a better understanding. We will discuss permeability today in terms of how it relates to viscosity, but we will not go into detail about the Clearwater reservoir quality at this time. Before getting into some of the mapping, let's take a look at some of the important factors in oil degradation, which are temperature, salinity, and inorganic nutrient availability. We will look at the temperature effect through various geothermal maps, salinity through analyzing water chemistry, and inorganic nutrient availability through the hydrodynamics and fluid flow through the formation. The figure here isn't overly important to get bogged down into, but basically it shows the rate of methanogenesis or biodegradation at different salinities and temperatures. The Clearwater Formation, as we will see, presents optimal conditions for degradation, but yet is not necessarily as degraded as these factors may indicate. Here we have a map of API gravity and geothermal gradient. The API map also has several other features on it that I will highlight now, as they will become important for the discussion moving forward. First off, we have two cross-section lines, which we will present in a bit to help discuss the potential migration pathways of oil and discuss the basin-wide hydrodynamics using this cross-section here. Further to this, there are two hatched areas on the map which demarcate the extent of the oil window for two important source rock formations, the Eksjö here in orange and the Nordig in blue. Now back to the API, which is colored from orange in the southwest, representing API values of greater than 50, and decreasing to dark green in the northeast, representing values of less than 10. The main feature on this map is the plume of higher APIs coming up from the southwest towards the Marten Hills and Nipisi area. Moving to the left is the geothermal gradient map. We see that the geothermal gradient is much cooler in the north than it is to the south. And we also see an area of high basement heat flow extending up from the southwest towards the Marten Hills area, like we observed on the API map. This hotter area that corresponds to an area of higher APIs may be indicative of potential migration pathways. On this slide, we have the same API map paired with an isotherm calculated at the top of the Clearwater A. Again, we see the hottest temperatures in the southwest of around 85 degrees Celsius, decreasing to less than 10 degrees in the northeast. Formation temperatures in the Marten Hills and Jarvie area are both around 30 degrees, and temperatures in other Clearwater fairways range from 20 to 30 degrees. The temperatures are all low enough for biodegradation to occur. Once again, the higher temperatures observed from the southwest, extending up to the Marten Hills area and east into Jarvie, point towards potential oil migration conduits. The next two slides are going to focus on the two cross-section lines that we highlighted on the API map. We will start with the southern cross-section here. Along this section, the Eksjö and Nordig are both mature close to each formation's respective subcrop edges. The edge of Eksjö maturity is here, and the edge of Nordig maturity is here. In this area, the Eksjö likely migrated up through the Wabamun and eventually into the Clearwater. The Nordig likely migrated up into the Wabasca, through the Wabasca, and into the Clearwater. The other two figures on this slide are from a paper, Berbesi et al. 2012, that was trying to determine the main source contributor in the oil sands. This paper, along with others, have indicated that Nordig oil, labeled as Gordondale here, is the main source of oil in the oil sands. This is due to the fact that Nordig oil is characterized as type 2S kerogen. This changes the kinetics of the kerogen and lowers the activation energy, which allows for this oil to begin generating earlier. This allowed for oil to be generated, expelled, and migrated into the Clearwater before the Eksjö even reached thermal maturity. Although this may have been the main source of oil, there was likely still multiple phases of migration from both the Nordig and the Eksjö. These various phases may help to explain the variation in oil quality from a source perspective. For example, the initial phase of Nordig migration would have been heavier oils as peak maturation had not yet been reached. These oils would have been more likely to migrate along warmer thermal conduits as we saw from the southeast towards Marten Hills and Jarvie. Later oil that was more thermally mature may have been able to migrate along thermally cooler conduits, perhaps filling reservoirs like Cadott. The only difference on this slide is the section line. This cross-section line is in the northern part of the study area. Here, the maturity limits for both the Exshaw and the Nordig are much further to the west. The Exshaw once again likely migrated up through the Wabamun, and in this area, the Nordig likely migrated through porous Mississippian units up into the Wabasca and into the Clearwater. It is interesting to note here that it is very likely that the same oil which migrated into the Clearwater in the Cadott area also migrated through the DeBolt. However, the oil in the DeBolt must have been degraded a lot more after emplacement than oil in the Clearwater. These cross-sections provide evidence of two potential source rocks for the Clearwater and possible migration pathways. The source of oil is only one factor in understanding the oil quality. However, it can provide extra context in predicting oil qualities in less developed parts of the Clearwater. The next component of this presentation is hydrodynamics. The main aspect of this section will be hydraulic head mapping. Hydraulic heads flow from areas of high head to low head and allow us to determine the flow systems within the Clearwater. To begin, we actually see hydraulic communication occurring from the Viking into the Wabamun. And as such, we have the Viking Formation hydraulic head map here on the left and the Wabamun on the right. Hydraulic head values in the Viking are higher than that of the Wabamun, indicating downward flow. We see complexities in the flow patterns in the west, which we will discuss in a few slides. But overall, we see up-dip lateral flow occurring from southwest to the north and northeast. We also can see that the Wabamun contours are quite consistent, and this indicates the porous and permeable nature of the Wabamun Formation in this area. Here we have the Clearwater hydraulic head map, which ranges from 650 meters in the southwest to 450 meters in the northeast. These head values are generally lower than the Viking, but higher than the Wabamun, once again indicating downward flow. This can be further demonstrated on a local scale with the cross-section to the right. This cross-section extends from the south to the north through the Jarvie producing area. And all of the wells here have multiple hydraulic head measurements, which further demonstrate that the Viking has higher heads than the Clearwater. For example, here, the hydraulic head in the Viking is 585 meters, and in the Clearwater, it's 488 meters. This indicates downward flow. At the same time as downward flow, the system is also experiencing lateral flow. This is demonstrated by looking at data points within the Clearwater Sea, where we have hydraulic head values of 523 meters here and 514 meters here, indicating lateral flow from south to north. Moving on from hydraulic heads into water chemistry. On the left is a crossplot we use to help call the data, as well as determine true formation brines and the meteoric water dilution trend. On the right is a map of Clearwater total dissolved solids. Salinity is lowest in the north and increases to the central and to the southeast part of the study area and decreases once again towards the southwest, where waters here are indicative of deep basin Kone waters. The Clearwater, as mentioned at the start of the presentation, is a marine and proximal marine deposit, and as such, the low salinity in the north represents an influx of surface recharge to the northeast, where the upper Manville is more closely connected to the surface. Low salinity areas show degradation, but so do areas of high salinity like in Jarvie. As such, salinity does not appear to be a main controlling factor on understanding oil quality. This hydraulic cross-section provides a three-dimensional visualization of the distribution of hydraulic head in the study area. Across the study area, we see downward recharge, particularly in areas of topographic highs, like the Swan Hills and Marten Hills. We also observe flow complexities in the west, which can be connected to the petroleum systems. There's a zone of higher pressure here in green, which can be connected to the edge of Nordig maturity and can be related to the generation and expulsion of hydrocarbons in this area. We also see a zone of underpressure to the west of here, which can be related to gas leakage in the deep basin. This interplay of fluids in the west causes complexities to the flow patterns. However, on a regional basis, we observe up-dip lateral flow to the north and northeast, along with downward flow as the porous Paleozoic formations and Grossmont aquifer act as a hydraulic low and draw flow down through Cretaceous sediments. Based on this cross-section and the hydraulic head mapping, it can be observed that the Clearwater and adjacent units form a dynamic conventional system. The dynamic flow system in the Clearwater, coupled with the relatively low salinity in many areas, may have adverse effects on oil quality by enhancing biodegradation. However, this is also likely influenced by the quality of the reservoir and the exposure of any given area to fluid flow. To this point in the presentation, we have discussed several factors that may influence oil quality in the Clearwater, from the petroleum systems and geothermics to hydrodynamics and water salinity. It is obvious that not a single factor can answer the question of oil quality. However, before we end off today, it is important to take all those factors we discussed and distill those thoughts down to a few crossplots to help bring some understanding to oil quality. On the left is a plot of formation temperature versus viscosity. And although there is scatter in the plot, when we break it down into producing zones, we do see that these two variables are related. And as formation temperature increases, viscosity decreases, generally leading to better quality oil. On the plot to the right is viscosity versus permeability times reservoir thickness, or KH. We have discussed the dynamic flow system that occurs within the Clearwater. However, the level of flow and exposure of the hydrodynamic system within any given area is controlled in part by the permeability of the rock. On this plot, we can see, in general, that higher permeability results in higher viscosity and therefore heavier oils. This suggests that high permeable areas may become more degraded than less permeable areas. So in conclusion, we showed that the Clearwater is likely sourced from both the Nordegg and Exshaw formations, and the different sources, along with multiple phases of migration, may help to explain the variation in oil quality. Of course, this is only one component of the story, and we also have to take into consideration the factors that may have affected the oil quality after oil emplacement. That brings us to the hydrodynamics component, where we observe that the Clearwater and adjacent units are in hydraulic communication with both downward and lateral flow. This dynamic system within the Clearwater, coupled with relatively low salinities in many of the areas, may have adverse effects on oil quality by enhancing biodegradation. Additionally, salinity does not appear to be a main controlling factor. All of this points to the complexity involved when trying to understand oil quality and provides insight as to why the Clearwater exhibits such large range of oil qualities, and the importance of using the petroleum systems and hydrodynamics as tools to help determine and predict oil quality. Further to that, we can conclude that oil quality is related to several factors, including the oil source and timing of migration, which may help to determine the viscosity and API of the initial oil emplaced. Formation temperature, which can be related back to basin geothermics, where an increased formation temperature generally relates to a higher quality oil. And finally, the amount of fluid flow the formation has experienced, which will enhance biodegradation. And this can be related back to the permeability of the reservoir, as we see an increase in permeability generally lead to lower quality oil, as the permeability increases the exposure of the reservoir to fluid flow. The Clearwater, despite having relatively low formation temperatures, is generally less degraded than underlying formations. This may be influenced by the lower quality of the lithic sandstone reservoirs of the Clearwater and may provide insight into future exploration and development of the Clearwater and similar formations. If you have any further inquiries about this presentation, please don't hesitate to contact anyone listed here, and I would now be happy to take any questions that there are. Thank you for your time.